Hi and welcome back to another LeetCode problem. I'm currently going through neetcode.io's neetcode 150 list, and I'm focusing on the backtracking problems. And I'm just practicing LeetCoding, right? So this is a little less than an explanation video. It's really just me, trying to solve it. And we've solved 3 problems so far, and I'm going to attempt to try to solve combination sum 2 now, which should be a variation of the first combination sum problem that I just solved. So let's see. And I have solved this before. Let's see, but a while ago. Okay, so right. Let's see if I can solve this one. So combination sum version 2. Given a collection of candidate numbers, candidates, and a target number target, find all unique combinations and candidates where the candidate number sums to target. Each number in the candidates may only be used once in the combination. Okay, the solution set must not contain duplicate combinations. Again, we have the same constraints. The target is a number larger than 0. The candidate numbers have values between 1 and 50. And the length of the candidate is also bounded. For the runtime analysis and space complexity analysis, we won't care about these upper boundaries. Otherwise, everything is constant space and constant time, right? So, yes, so the only difference seems to be to the previous problem that now we can only use candidate numbers once. That's what that means, right? But let's have a look here at this example. So we have the candidate numbers and they're unsorted. 10, 1, 2, 7, 6, 1, and 5. So also duplicates. So I want to see if we can use those duplicates, and the target is 8. Right, so, okay. Right, so what combinations can we pick? So 10 is larger than 8. 1 plus 2 plus 7 is larger than 8. 2 plus 7 is larger. 7 plus 6 is larger than 6. So I think, so the first thing that I'm noticing, I find it difficult to systematically pick numbers. I think what we will have to do is we will have to sort them. And when we sort them, I think then it becomes much easier. So let's try this. 1, 1, 2, 5, 6, 7, 10, right? And now it becomes easier for me to see what to do, right? I'm going to use an approach that is similar to the one that we had in the previous combinations of problems. So I'm just gonna add numbers until I reach targets or if I'm over the target. So 4. So now we're at 9 if I pick this. So this is 9. This is not a match. So next I start at number 1. Skip the next one. Start at 2, 5. So we're actually at 8 now. And that is a match. Cool. And now we start at 1, 2. We skip the 5. We go to 6. Now we are too large again, so we can't do that. Okay, so now next, what shall we do? We start at 1. We go directly to 5, so we have at 6. Now we add another 6, so that's 12. That's too large. Okay. Next, we're going to start at 1 and 8. That is 9. That's also too large. All right, next iteration. So now we pick this one, this 2, this 5, and it's 8. That's okay. Now, is the 1, 2, 5 twice in here or once? 1 to 5 is only once. Interesting. So if we sort them, that means we can skip over elements that are the same, right? We could skip over them. Yeah, that's probably the twist to the problem that we have to take care now. I think what we could do is, because we don't really want to skip over them all the time, right? We might need them. So like here in 116, we both need them, the consecutive ones. But what if when we pick a number, well, let's say when we're here, right, we could check if the previous number is also a 1. And if it is, we could skip the whole thing. But only when we start at this number. So yeah, let's say we I'm not quite sure yet how to do that, but I think let me just write, sometimes helps to just write the code that we know that we need. So we're going to need a helper function again. We're going to need basically a starting index from which to compute the reigning combination. If you've seen the previous video, then you know why I know how to do this. Combination and no, wait, selection, and we have the current sum that we will pass in. Right, so now we have the case if current sum equal target, that's when we know that we have a result, right? And we need to add the current combination to the result. Result.append the current selection like so. Otherwise, if current sum is smaller than target, we need to continue selecting elements, right? And we call the helper. The selection is empty in the beginning, and the sum is also empty in the beginning. Right, so those are the basics. So in case the current sum is larger than target, we're just not going to do anything. But if it's not, we have to continue picking the next element. So I'm just going to write the code for picking the next element and then explore how we can avoid selecting the same combination of numbers twice. As we would with the 1 to 5 here. 1 to 5 is 8. But then we could also, well, we have this 1 to 5 and we could have that 1 to 5. All right, so we'll have a little for loop here. For I in range start. And well, we need to iterate until the start, till the end of the candidates array. And what we will do is we will pick this element in position candidates I, and we will add that to our selection. And we will have a recursive call here, and then we'll have a selection pop here to remove it again. That is the backtracking part. And we would call the helper here recursively. Start is now I plus 1. Because we cannot infinitely many times reuse the same element, we can only use it once. In the combination sum 1, we had this actually set to I, so that we can select an element an infinite number of times. Helper, and we're going to pass in our selection, and we're going to pass in our current sum plus the value of the candidates, and then we pop that out again. So now we need to take care of that step. And how do we do that? Is there something we can do here? So if Huh. Well, so that's now the difficult part, I guess. So at this point, when we are here, we have in our candidates, let me just rebuild this, because it has already escaped my short-term memory, how that exactly worked. So the target was 7, or no, 8. And I just remembered we need to sort this, right? Sort. I mean, if we don't sort it, we'll just get all of the different combinations. But I want to sort it so that I have an easier time to identify when we're adding duplicates. So we should always pick the first element. So we will have in candidates, we will have 1. Sorry, 8 was 5, 6, 7, 8. So we have 1, 2, and 5 in candidates. This is one example. Another case that we could have is we have 1, 2, and 5. What would be the difference between those two? Well, here we know that there's a 1 here. Well, we should be allowed to pick 1, 1, 2, 5 because that is over, so that's fine. This is actually equal to the target. This is also equal to the target. So we don't want to prevent selecting the same number twice. But what we want to prevent is, well, we know that earlier we tried this, didn't work. Then we tried that, and that actually did work. Now, when our start value, so in the first case, the start value is here at position 0. And now the start value is at position 1. Well, we know that we had, can we use that the predecessor is here? So that when we have the case that we start at the position where this one is, but it has the same value, we could skip that safely because we know we already had a case before where we picked a 1. And not only that, we also had the case where we picked both 1s. So that means we can ignore this case now because we already had a case where we picked 1, 1. So if we were to say if candidates at position I is the same as before, we could detect that case and we could just skip over that case. That's what we could do. That's what we could do, I think. Yes, I think that's what we could do. And let's see. Maybe we should use this as an example and just try it out. So we're going to sort these numbers first. So we have a 1 and lots of 2s and a 5. So let's just walk through our code with this example here, this one. So result is empty. We're going to sort the numbers. We get them in this order. Now helper starts at index 0, start is 0, selection is none, the current sum is 0. This does not catch, so we're in this case. So now we start iterating from 0 to 1, 2, 3, 4, I guess. Now, so this should be I minus 1. Okay. So this will immediately crash because this tries to access an element outside of the array. And our reference is start, right? So we actually have to check against that starting reference, I guess. So if, yes, if I is larger than start, and otherwise, yeah, otherwise it won't work. And also, yeah, so we just check if, wait, or does it only work in the first case? Well, we need this for the first case, that's for sure. So let's just continue and see what happens. So we append 1 to our list of candidates, then we do the recursive helper. Our start value now becomes 1. The selection contains the first element. The current sum is 1. Now it gets interesting. If we left it this way, so now in the first iteration, I is actually equal to start, and we're going to ignore this. So then we add 2 to our selection, and we go back into the recursion again. No problem. Next, we add another 2, because this doesn't catch. We add another 2, no problem. Okay, so we do this a couple of times until we run into the problem that it's larger than, oh no, actually we run into the case where it is equal to 5. So then we add 1, 1, 2 to our result, right? Which is exactly these 1, 2s. And then we return from our recursive call. And now we are looking at this combination of values. So we're adding another 2. But now this cage actually catches. So I is 0, 1 is 3 and start is 2. So this catches, and they're the same. So we're going to ignore this case. Ooh, nice. So we're ignoring this case and we're continuing until this one is ignored. I actually didn't. Okay, back this. And then we try this case. And 5, 6, 7, 8 is larger than 5. So no results. So we're backtracking. So now we have this case where we advance our second, well, the index in this recursive call. So now we select 1, 2. So start is pointing at 2, and that's fine. We can select that 2. Yeah, so this case doesn't catch. In this case, we can select the 2. The next value would be another 2, which is allowed. Well, which is not allowed in the recursion. Which is not allowed in the loop, but it is allowed in the recursion. Yeah, I think that's the key point. So in the loop, we do the checking and the skipping, but whenever we do a recursive call, we don't mind if we're using consecutive equal elements. I think this should work. I'm just going to run it through the tests. Okay, current sum as a typo. All right. Let's try again. Okay, and the test cases pass. Nice. Okay, now comes the big reveal. Does it actually work? It does work. Okay, cool. And so now I completely forgot the runtime analysis. Well, what time and what space do we have? And space. So in terms of space, there isn't really a limit, right, on how many numbers could sum up to the target value. Let's say the target value is well, what would be the worst case when we can form as many combinations as we want? That is when we have, I suppose, an array of ascending numbers, and the target sum is equal to the sum of the first and the last, the second and the one before the last, etc. I think that would be the worst case, wouldn't it? Where every element can be part of a sum. But that would still be linear. So I think we will have linear space. Because as soon as we pick more than two numbers, it's basically n over 3 different possible combinations to add up to a value, I think. Yes. And well, in terms of time, well, we call our helper, right? And in each recursion, we're advancing. Well, first of all, we're doing the sorting, right? So that's for sure n log n. And then we're doing the backtracking. And that, I think, is still 2 to the power of n, because we're considering all combinations of candidates with each other, all of them, in the worst case. Right? If everything is 1 in the array, that's the worst case. All elements are 1, and the target is exactly the sum of all elements. That means we will iterate over all of the elements in every recursive step. But we will compute literally all different subsequences of the array. So I think that's 2 to the power of n. Which is of course larger than n log n, so it's of 2 to the power of n time and over on space. That's what I think. Right, that's it.